Hello, everybody. So in this video, we're going to continue the discussion on the viscosity of fluids and the types of fluids that we deal with. So what we mentioned last time about the types of fluid was or the equation that describes the fluid behavior is the Newton's law of viscosity, which we discussed last time, where we have the viscosity as the constant of the proportionality between the shear stress and the shear rate. We said that this is called the Newton's law of viscosity, and we said that the fluids that follow the Newton's law of viscosity are called Newtonian fluids, and these are the very common fluids that we deal with on daily basis, like water, like air, like honey, like oil. These are Newtonian fluids. They behave this way. There are other fluids that don't follow Newton's law of viscosity, and we are going to discuss them today, or in this video. But I want to first highlight what we mean by Newtonian fluid in a specific way. So the Newtonian fluid satisfies two criteria. These two criteria are related to the shape of the relation between the shear stress and the rate of deformation. For any Newtonian fluid, as we saw before, for air, for oil, and for water, they all have or two things in common. First of all, that they all are linear relations. So they have constant slope, regardless the value of the shear stress or the value of the rate of deformation. This slope is constant everywhere. Okay, so it's a straight line. The second thing, that all of them pass by origin. So they all pass by the origin, which is 0, 0. And these are the two criteria that must be satisfied for a fluid to be a Newtonian fluid. So what we're going to discuss now is the other types of fluids that don't follow or don't satisfy these two criteria, which we call non-Newtonian fluids. And this is one interesting thing about these types of fluids, that, and as I told you, the most of the fluids that we deal with on daily basis are Newtonian fluids. So it's a little bit hard for you to imagine or understand that these fluids that we are going to discuss are actually fluids. But this is the truth. So the first type is called the shear thickening fluids. Shear thickening, the word thickening means that the fluid thickens, meaning that the viscosity increases. So when we say that it's a shear thickening fluid, it means that the fluid thickens with shear, which means that the viscosity increases at high shear stresses. Which is, of course, it means that at low shear stresses, the viscosity is not going to be high. So this is what it means. This video that you are going to see here is an interesting one, and this is one of the very famous shear thickening fluids. This is, by the way, it's called oblique. Oblique, it's a mixture of cornstarch and water, and it behaves in a very strange way. So, and by the way, if you search for this word online, you will find a lot of videos, very interesting things, and like people make a lot of events just using pools filled with this oblique. So if you see that here, it seems that at high shear stress, when it's exposed to very strong shear, like hitting with a fist, or as you will see later, hitting with a hammer, it behaves as a solid, which means that the viscosity is very high. But if the shear stress is low, it's a liquid. And for this case, jumping on this fluid is like a lot of shear. After stopping this shear, it behaves as a normal fluid. So this is like an interesting thing. The viscosity seems to be very high at high shear stress and very low at very low shear stress. So the shape of the relation between the shear stress and the rate of deformation is as you see here. Okay, and just to understand how this reflects what we saw in this video. At very low shear stresses, a very low shear stress can lead to high rate of deformation. And if you want to apply like high deformation rate, this is easy to be done with very low shear force. Okay, and as the shear stress increases, the rate of deformation increases as well. And if you want to apply to achieve this rate of deformation, you have to apply very high shear stress compared to this. You can also look at this from the slope. We know that the slope is the viscosity, so the slope here is very small, which means that the viscosity is small or low viscosity, but here the slope is high, which means that it's a region of high viscosity. So the viscosity here is higher than the viscosity here. So the high viscosity at high shear stress is what makes it shear thickening fluid. On the other hand, we have the opposite, which is the shear thinning fluids. Shear thinning fluids are fluids whose viscosity decreases with the increase in the shear stress or the shear force. And these are sometimes called pseudoplastic. The very famous example is ketchup. You all know that ketchup is hard to get out of the bottle, and if you want to just flip the bottle and try to put the ketchup to flow by itself, it will never flow. For it to flow, you have to do, as in this video, you have to apply some shear force, and this shear force is going to reduce the viscosity of the ketchup, and it will flow. And I think you saw this happen to you many times, that you will put more force than you need, and then the whole bottle will be emptied in just 1 or 2 hits. So you have to be careful when you apply the force. You need to know how much shear force, so that the viscosity doesn't get very low and it flows more than what you need. The examples of this are, as I said, the ketchup, the mustard are the same, or both shear thinning fluids. Polymer solutions are one of the things. The paints, this is one of the very famous examples. It's one of the desirable qualities of a good paint, that it's easy to spread on a surface. So if the shear is not low while it's being painted, it's going to require a lot of force to spread it on a surface, while having the paint as a shear thinning fluid, you can spread it easily on a surface with an irregular force without putting a lot of stress on the paint. And now if you want to see how this curve will look like in the for the shear thinning fluids, it's going to be as you see. So here at very low rate of deformations, if you want to do small rate of deformation, we need to apply very high shear stress. But if and this is what you can see here from the slope here, the slope is very high here. While if you exceed some specific shear stress, the rate of deformation can be achieved with, it's not small of course, but it's intermediate force or shear stress. Okay, and this is what you can see here. The viscosity here is lower than the viscosity here. So these are the first 2 types. There is one third type of non-Newtonian fluid, is what we call the Bingham plastic. The Bingham plastic has one different thing. So again, if you compare these two, the shear thinning and shear thickening curves, to the Newtonian fluid curve, you will notice that they all pass by the origin, but they are not linear curves. Plus, it's not linear here, and the same for the shear thinning, it's not linear here. So this is the deviation from the Newtonian fluid profile. For the Bingham plastic, it is different. For the Bingham plastic, it is linear, but it doesn't pass by the origin. So it behaves as a solid at shear stresses below a specific value. So that if the shear stress is below this value, it behaves as a solid. You apply force or you apply stress, and nothing happens. It doesn't flow. It doesn't deform. After some specific shear stress, it starts to flow with a constant viscosity. But before this shear stress, it's not flowing. So the very famous example of the Bingham plastic fluids is the toothpaste. Toothpaste is it's in the tube. You try to get it to flow outside the tube, but it doesn't, unless you apply, or until you apply specific force that is enough to push the toothpaste out of the tube. Okay, so this is a shear, it's not a, it's a Bingham plastic fluid. So these are the very famous three types of non-Newtonian fluids: the shear thinning, shear thickening, and Bingham plastic fluids. One last thing I want to cover here is the dynamic and kinematic viscosity. So the viscosity that we saw in Newtonian's law and that we discussed many times before is we called it the dynamic viscosity, or just the viscosity. There is another type of viscosity that we describe or we use. It's called the kinematic viscosity. The kinematic viscosity is combining the density and the viscosity in one term, and it's given the symbol nu, and it is defined as mu over rho. If you check the units, it's kilogram per meter second over kilogram per meter cube, so it's going to be meter square per second. This is the SI unit, and the CGS unit is called Stoke. Stoke is centimeter square per second. So one Stoke is 10 power minus 4 meters square per second. So it's very common to use for some applications that you are interested in the combination of both the density and the viscosity in one unit, which is the kinematic viscosity. So I'm going to stop here. Next time, inshallah, we are going to discuss the effect of temperature on the viscosity and how it differs from solids to from liquids to gases. So I'll see you then, inshallah. Goodbye.